Alright, so in this problem we have a hoop rolling down an incline and then off a table, and we have to figure out some various kinematics quantities, so accelerations and speeds and distance traveled. In this problem we'll have a relatively long video, not because it's a long problem, but because there are many different approaches. I'm going to do two of them, the two that I think are the most likely that you would pick. But keep in mind they're separate. You don't have to do both. You have to just pick whatever you're most comfortable with. So when I look at parts A, B, and C, the first thing I think is kinematics, because I see acceleration, speed, distance traveled. And when I think kinematics, I'd be thinking forces. And so if I do that, then my first step is going to be to draw a free body diagram. So this is going to be starting with part A right here. So this approach is going to be using forces and kinematics equations. And so I start with a free body diagram. We have our hoop, and I have to be careful to apply all the forces sort of exactly at where they are acting, right? And I'll draw in red a pivot point, or the point we're rotating around is the center. So now I need to use Newton's laws to figure out accelerations, right? The net force, I'm going to say this is net force in the x direction, the down the ramp direction. Right? That'll give us the acceleration. This is, right, exactly what we want. That's the acceleration of the center of mass. And so if I start that, I'm going to write two things. I'm going to notice it's going to be mg sine theta. That makes me go down the ramp. But friction opposes that. Right? We know theta, but we don't know the friction force. So I can't solve this by itself. And so there's a couple things that could happen when you get to this point. The first is you could conclude that I've done the wrong thing. This is not possible to solve this way, so I have to try something else from scratch. And we'll come back to that approach in a second. The other thing you can conclude is, well, we know more information than this. We also know something about it rolling, right? The net torque was I alpha. And we know there's a relationship between alpha and A. So the net torque, when I look at that, there are three forces, but only one, right, specifically that one, is going to exert a torque, because the other two, one acts at the center of mass, the pivot point, and one goes directly through it, so they both would give zero torque. So this is just F times R, right, 90-degree angle. I, we know what that is. We're told rotational inertia, mr squared. And then alpha is going to be A over R. Right? That's the relationship for something that rolls without slipping. And so I can cancel some stuff. We notice there's enough R's to cancel them all out. And so we find that F equals ma as well. Right? Okay, so now, if I've decided to keep going with my kinematics approach, I see something very nice, which is this can go right in there, and now we can solve. So mg sine theta minus ma equals ma. So I now see there's an m in every term. Cancel. Which is good, right? This should not depend on the mass, because it's gravity that's really making it go down the ramp at all. And we combine the two a terms, so we get g sine theta equals 2a, right? Or a equals g over 2 sine theta, right? So that's our answer to part A. Now, part B is pretty straightforward. We know the acceleration, we know the distance we travel, we don't know anything about time, so I'm going to pick the kinematics equation that doesn't involve time. Right? V final squared, V initial squared, plus 2a delta x. So V final, that's what we want. V initial is 0. We know the acceleration. and delta x is L, the distance of the ramp. So those 2's will cancel out, and we can take the square root, and we'll get v final square root of GL sine theta, right? And so that's A and B. So that's one approach, right? Forces in kinematics. But remember, we got to a point right here. When we saw that equation, we realized we had two unknowns. And so maybe you saw that and you thought, okay, I don't really know how to do that in any other way. I can't figure this one out yet. But you look at part B and you realize that when you're asking about speeds, that's oftentimes an energy conservation sort of thing. I could easily figure out the speed at the bottom of the ramp without caring about the acceleration at all, because I know the energy I start with, and I know that it's rolling, so I'm going to get two types of kinetic energy at the end, right? So if we solve part B and thought to ourselves, okay, well, I couldn't figure out how to do it with forces and accelerations, but I can do part B regardless. Let's do that and see what happens. Right? So we say energy is conserved. Our initial energy is mg mgh, which we'll come back to in a second, right? And then at the end, we end up with two kinetic energies, 1/2 mv squared plus 1/2 I omega squared. And so when I look at that diagram, we have theta, h, and L. So h, actually rather let's write it this way. So yeah, h over L equals sine theta, or h is L sine theta, so I can simplify that. So let's plug in all this kind of stuff that we know. So mg L sine theta, 1/2 mv squared, right? V is what we want, so we'll leave that. We know the moment of inertia, and we know a relationship between omega and v. Right? So, now we can cancel things. There's a mass in every term. We have an r squared and an r squared. So we can cancel those. We can clean this up a bit. So since we know we want to solve for v in the end anyway, actually let's leave that as it. So gl sine theta. So we have a 1/2 v squared and another 1/2 v squared, which is just v squared. And so we can find v, once again, quite quickly. So we did part B, and we didn't get part A yet, but now hopefully you know a bit more about the problem. We know the speed at the bottom, we know the speed at the top, and we know the distance we travel, so we can use kinematics again. Right? We don't need to do this with forces at all. I can say v final squared equals v initial squared plus 2a delta x, and now we just sort of do the same thing but backwards. Right? So A is now our unknown that we solve for. Right? We can cancel the L's, and we divide by 2, and we get A has got to be g over 2 sine theta. Right? Once again, exactly the same as we got before. So either one of these approaches works. Right? It's always a good idea to look at the whole problem to see if a later part might help you with an earlier part. They aren't always sequential, or sometimes there's also different sequences that you can do. So parts A and B you can kind of approach in either order, right? Either of these two approaches are separate. You should not do both, right? You should sort of pick which one you're comfortable with and go with that. Either way, for part C, when you get the speed that it's traveling at the bottom at, now we're doing projectile motion, right? We have our object with that speed v, and it's going to follow. Let's see if I can make that a little neater. It's going to follow a parabolic path, and what we care about is this distance d, right? And we also are told that this is height h. So we have to use vertical kinematics to figure out how long it takes to hit the ground. And we know the acceleration, we want to know the time. This is pretty characteristic of any projectile motion question. We have to figure out the time somehow. So that's going to be, actually Right, we start at position h, we end at the ground, so that's 0. So 0, actually, I'll just write the initial equation. So y final equals y initial plus v initial y times t plus 1/2 ay t squared. That's really messy, but anyway. So we plug this in. Our final position, 0. Our initial position is at height h. We have no initial vertical velocity because the ball comes off the table horizontally. Oops. We know the acceleration is negative g, right? And then t squared we can solve for. So we rearrange that. We get t is the square root of 2h over g. Now, we use kinematics again for the vertical motion, or the horizontal motion. In the horizontal direction, we have no acceleration. We have a constant velocity and a time, right? How long it travels. So the distance we travel, d, is velocity times time. And we got the velocity from before. And we know the time from what we just calculated. Right, so this can be simplified a bit because our square roots of g are going to both cancel. Right, so we get the square root of 2hl sine theta. Right, and that's how far our horizontal distance is. Right, no matter how you did parts A and B, right, as long as you get the velocity, you can do part C. And again, as always, if you can't figure out that correct velocity, get an answer to part B somehow, and then just use it correctly in part C. Okay. All right, so part D. Now we're taking the hoop and we're replacing it with a same mass, same size disk. And we want to know how the distance compares. And this is an explanation part, so you don't have to really do any math. In fact, you probably shouldn't. So the answer is, first of all, that it goes farther. And I think that this one is best explained in the concept of energy conservation. That's really the easiest way to talk about it. So if you have the same force down the ramp, which we do, right? Gravity is what makes it go down the ramp at all. And therefore the same torque that makes it rotate going down the ramp, then the smaller moment of inertia leads to a bigger acceleration, right? So I goes down from the hoop to the disk, so alpha must go up, right? If alpha goes up, then we know that since alpha is related to A must go up. If we travel the same distance and have a bigger acceleration, then V must go up. We didn't change anything about the motion when it falls off the table, so that time is the same. So if the velocity goes up and the time is the same, then D has to go up. Right? And that, I think, roughly answers it, right? You should write that as sentences, not my list of variables and arrows, but that sort of explains the concept.